This animated diagram plots the baseline objective of lunar sample return. On Apollo 11, the primary directive was a quick contingency grab yielding 21.5 kilograms. By Apollo 17, the payload surged to 110.5 kilograms, alongside a proportional parallel growth in specialized tool weight. Operating in the lunar environment meant engineers were fighting physics from the start. They were designing hardware for a hard vacuum, where fine, highly abrasive dust coats and degrades mechanical seals almost instantly. Then there was the human element. Inside a pressurized spacesuit, an astronaut operates under severe kinematic restrictions. Basic movements, like bending over or gripping a handle, become exhausting battles against the suit's internal pressure. Extracting pristine extraterrestrial stratigraphy relies on a rapid, iterative re-engineering of the entire fieldwork process to overcome those physical barriers. When faced with limited time on an alien surface, the immediate instinct is to collect the largest, heaviest rocks available to maximize the sheer mass of the return payload. However, large, monolithic bulk rocks actually offer relatively low geological diversity. They represent a single event or formation, limiting the breadth of analysis scientists can perform on a given sample. This bar chart maps out the scientific community's proxy for research interest, allocations per gram. Assuming more researcher requests equal higher scientific value, the data shows bulk rocks have minimal allocations. Exponentially higher demand is concentrated entirely in deep cores and soil fragments. This data forced a shift in mission priorities. The engineering goals shifted away from grabbing surface rocks and focused directly on the complex task of extracting high-diversity soil and deep vertical stratigraphy. Capturing that vertical stratigraphy meant driving hollow tubes straight down into the lunar surface to pull up intact cross-sections of geological history. Early missions relied on 2-centimeter diameter drive tubes with thick walls, but the dense, interlocking grains of the lunar regolith created immense friction, causing physical failure as astronauts struggled to drive these tubes deeper. By Apollo 15, engineers deployed a precise mechanical solution. They widened the tubes to 4 centimeters and significantly thinned the walls. This reduced the displacement of the dense regolith, facilitating easier penetration. But solving one physics problem created another. Driving these larger diameter tubes required more kinetic energy, meaning the standard geological hammer was no longer sufficient. The tool underwent specific geometric alterations. Engineers added a larger headmass near the shaft, a modification engineered for pounding the flat tops of the new core tubes without glancing off. Alongside deep cores, researchers required high-diversity soil fragments over large bulk rocks. To meet this demand, later missions introduced a specialized sampling rake. An astronaut dragging this specialized tool through the thick lunar regolith achieves a statistical sampling in a single, continuous motion. The tines let the fine dust fall away, while simultaneously capturing a wide array of small, diverse lithologies from the surface. The specific physical constraints of the regolith dictated the exact geometric changes to the hardware. Those iterative adaptations increased the scientific yield for every kilogram returned to Earth. There is an inherent paradox in planetary sampling. The hardware required to access a pristine environment acts as a massive, localized pollution source. From the moment of arrival, the vehicle and the human operator actively deposit invisible chemical noise onto the barren surface. The vehicle itself introduces heavy organic vectors. The large descent engine exhaust blasts combustion products directly into the sampling zone, while the lunar module continuously outgasses volatile compounds into the vacuum. The astronauts add their own highly localized vectors. Their pressurized suits leak, their backpacks vent gases constantly, and walking sheds fabric particulates directly into the soil. To preserve the strict scientific integrity of the collected samples amid this contamination, NASA implemented a strict materials restriction policy. The rule was absolute. Any material, container, or tool that touched a sample was restricted exclusively to stainless steel, aluminum, or Teflon. Because the act of traveling to the moon pollutes the sample area, extracting the true geological signal requires extreme, highly defensive curation protocols once the valuable material arrives safely back on Earth. Upon arrival at the Lunar Receiving Lab, defensive protocols dictate that materials are handled exclusively in pure, dry nitrogen environments to block terrestrial atmospheric contamination. The deep soil cores represent the highest value samples in the collection, and accessing the data inside them requires a specialized extraction methodology. This technical image details horizontal dissection. The soil core sits flat within an aluminum tray. Curators use small metal tools to peel away the regolith millimeter by millimeter, preserving the original stratigraphy against the ruler. The removed material undergoes immediate subdivision and sieving. Maintaining exact spatial and depth relationships within the core is critical. The exact position of a grain dictates its long-term exposure to solar wind and micrometeorite impacts over billions of years. Lose the physical coordinates and the scientific record is lost. Once the initial layers are gently removed, the remaining peeled surface of the core is stabilized using specialized epoxy impregnation. This binds the delicate granular structure into a solid block, which is then sliced into cross-sections exactly 30 micrometers thick. These microscopic thin sections allow researchers to conduct detailed petrographic analysis and precision electron beam scanning. Translating a raw tube of extraterrestrial dirt into readable scientific data requires advanced subdivision methods that are just as rigorously engineered as the complex flight hardware that actually went to space. There is a sharp functional distinction between the temporary transport containers used in flight and the permanent architecture required for ongoing curation. The Apollo lunar sample return containers were highly specialized pressure vessels, but their design mandate was temporary: survive the violent journey back to Earth without breaching. The modern standard demands continuous preservation inside hurricane-proof vault storage. This photographic source displays the type of specialized nitrogen glove box environment used to maintain that isolation. Decades after the missions ended, any current subdivision, weighing, or handling of Apollo materials still takes place entirely within these pristine, sealed environments. The curation environment is an active, ongoing engineered system, a continuously operating laboratory designed to protect the samples from Earth's atmosphere. The entire process follows a strict causal chain. Extreme lunar physical constraints forced rapid iterations in tool design, and those precise iterations enabled the collection of deep core stratigraphy. This established the baseline design lessons for all future extraterrestrial containers. They must be reliably openable after spaceflight, and their seals must survive infiltration by highly abrasive dust. Likewise, the tools themselves must be operable by human hands fighting the stiffness of a pressurized suit, and they must be manufactured exclusively from chemically acceptable materials. Effective curation requires the same rigorous oversight of the collection and handling processes as it does the material choices themselves. These Apollo-era lessons form the baseline parameters for the engineering challenges currently facing modern Mars and asteroid sample return missions. The ultimate legacy of the Apollo program is the multi-generational curation architecture that protects its harvest. That system allows those 382 kilograms of material to continually yield new scientific discoveries today.